Hello, my name is Renat Abdrastov, and I'm presenting interactive modeling of volumetric musculoskeletal anatomy. My collaborators are Sangbei Bang, David Levin, Karan Singh, and Alex Jacobson, and we are part of the DGP lab at the University of Toronto. Animating physically realistic effects like muscle bulging, skin sliding, and wrinkles without an explicit musculoskeletal structure is challenging and requires skilled and tedious manual effort to achieve high-quality results. However, user-friendly solutions to the problem of creating a musculoskeletal structure that is suitable for character modeling and animation are relatively unexplored. The most common approach used in the industry relies on using sculpting software like ZBrush to model every muscle. However, this approach is time-consuming and is out of reach for users who are not familiar with sculpting software like riggers, animators, and researchers. Alternative approaches like Maya Muscle require a tedious parameter tweaking. These methods make it hard to produce intersection-free muscle shapes that conform to the skin surface. If muscle shapes intersect between each other or with the bone geometry, then that could cause issues during the simulation. Additionally, often artists would load the skin mesh and need to sculpt the muscles to conform to the skin layer. Fiber directions play an important role in simulation by defining the directions the muscle contracts. Fibers tend to point in the same directions as gradients of hypothetical flow from one end of the muscle to the other. Currently, artists need to manually mark origin and insertion points to approximate the fiber field. Making incremental changes using these approaches is tedious and hinders the fast exploration of character design. In our work, we take a very different approach, and unlike previous methods, we do not model individual muscle shapes as geometric primitives. Instead, we adopt a volumetric segmentation approach where every point in our volume is assigned to a muscle, fat, or bone tissue. We provide an interactive modeling tool where the user controls the segmentation via muscle curves, and we visualize the muscle shapes using volumetric rendering. Muscle curves enable intuitive yet powerful control over the muscle shapes. This representation allows us to automatically handle intersections between different tissues and automates computation of muscle fiber fields. Based on this volumetric muscle representation, we build tools that greatly simplifies the creation of musculoskeletal geometry and can be used by non-modelers. The user starts by loading a skin and skeleton mesh. If the skeleton mesh is not available, we provide a skeleton builder tool to quickly generate the skeleton. The user then generates the skeleton by using a pre-existing library of bones that are adjusted to fit the skin mesh. The user generates a network of muscle curves that allow to segment the volume into different tissues. Finally, we developed an algorithm to convert our volumetric segmentation into tetrahedral meshes that can be used for downstream tasks. We group all bones into three different types. A cylinder bone is a type of a bone that can be represented as a line segment, for example, arm or leg bones. A cylinder-type bone template is pre-rigged with 2-point handles and is deformed according to the line the user draws. Curve bone is a type of a bone that can be represented as a curve. For example, a spine can be described as a sequence of vertebrae bones placed along a curve. When the user draws a curve, we feed a spline into given points and distribute the bone template along the spline. A shape bone is a type that cannot be represented as a line segment or a curve. Essentially, it describes all the bones with complex shapes. We place the shape bone using local fitting at the user-specified region. Let's first see our skeleton tool in action. To create muscles, the user draws curves. Skeletal muscles require an origin and insertion points where the muscle tendons are being attached to the bone, and the user is being able to control the shape of the muscle using the control points. Let's see a full modeling session to get an idea of what our muscle tool does. And now let's get into more details of how this tool works. As you saw in the video, the user draws a curve for each muscle. In our interface, we expect the user to always begin and end the stroke over the bone surface. The first and last points of the curve are automatically projected via raycasting onto the surface of the bone to find their corresponding 3D coordinates. The depth value for all the points drawn in between is ambiguous, so we simply linearly interpolate the depths of the first and last points. Because we want the curves to be easily editable, we feed a Catmull-ROM spline in a least squares manner with 4 control points by default, 1 for each endpoint and 2 along the curve. The user can easily add or remove control points. Each control point is augmented with an additional attribute representing a tissue value. Users can adjust the tissue value to shape the muscle. Now, given that we've created this muscle network, how can we generate muscle meshes? Well, first let's look at this problem in 2D to make it easier to visualize. Let omega denote our 2D domain defined by the circle, which we can think of as our skin mesh. We're also given 2 muscle curves within the domain. Our goal is to find scalar muscle functions f1 and f2 for each muscle curve that describe the likelihood of any point in our domain to belong to either of those muscles. Take the first muscle curve, for example. We define some tissue values at each point of the muscle curve, and now we want to smoothly diffuse those values away from the curve such that they become 0 on the skin boundary and 0 on the points of all other muscle curves. In our case, we only have one other curve. And the same idea for the second muscle curve. Similarly, we define a fat function f of s that describes the likelihood of any point to belong to a fat layer. The fat function is diffused from the skin surface using the fat scalar value defined by the user. To compute these muscle functions, we propose to define them as minimizers of the Dirichlet energy subject to constraints. We define M as the total number of muscle curves and sum the Dirichlet energies of all muscle functions over the domain, where matrix AI is an optional user-defined diffusion tensor field which biases the direction in which material flows at any point in space. We'll talk about this tensor more in the future. Since fat diffuses isotropically, we write it as a separate term. And here are our constraints. First constraint ensures that we respect the user-specified tissue values at the muscle curves. The second and the third ensures that each muscle function goes to 0 at the skin boundary and at the points that belong to other muscle curves. And finally, the last 2 constraints ensure we respect the user-specified fat value at the skin boundary and that it goes to 0 at all the muscle curves. Because we're working in 3D, we first need to generate the tetrahedral mesh from our input skin mesh and bone meshes. We define the tetrahedral mesh using 2 matrices, the matrix containing the indices of the TEDs and the matrix of the vertex positions. The muscle splines usually do not coincide with the vertices of the tetrahedral mesh, and to discretize the splines we need to identify a set of tetrahedrons that contain each muscle curve. For each tetrahedron and each muscle curve passing through it, we identify a point on the curve that is contained inside the tetrahedron. In practice, we choose the point to be the midpoint of the curve segment bounded by the tetrahedron. We call this point a collocation point. For each curve, we stack all collocation points in a matrix and compute the tissue value for each collocation point by interpolating values at control point. We use barycentric coordinates to compute the tissue value for each collocation point based on the tissue values at the vertices. So DIT here is the tissue value for the collocation point CIT. Bj is the percentage coordinate of the collocation point with respect to vertex j, and dj is the tissue value at vertex j. Stacking the barocentric equation for a set of desired values of collocation points into a matrix constitutes a linear equality. Here, for every muscle curve, we have a matrix B of I, which is a sparse matrix of stacked barocentric coordinates of collocation points for all curves. Di is a vector of stacked tissue values for all collocation points for all curves. So we can now write the discrete version of our Dirichlet energy and our constraints. Here, Li tilde is the anisotropic Laplacian defined using gradient matrix G, the mass matrix M tilde, and the matrix AI. Lc is the standard cotangent Laplacian. This term represents the constraint of a tissue value at the collocation points, and this term represents the constraint of the function to have a value of 0 at all collocation points. And finally, the two hard constraints representing tissue values at the skin vertices of muscles and fat functions. Alpha parameter defines the trade-off between smoothness of the resulting scalar field and representing the tissue value at the collocation point. Because the collocation points are not necessarily located at mesh vertices and many may appear in the same element, using soft constraints avoids overshooting. So by solving this quadratic minimization problem, we can find the value of each muscle functions at all vertices of our tetrahedral mesh. Each point in our volume will either belong to a muscle, bone, or fat. The fat is visually represented as an empty space between muscles, skin, and bones. The points that belong to the bone tissues are simply all of the points that are constrained inside tetrahedrons comprising the bone geometry. So we only need to differentiate between muscles and fat. We treat the muscles and fat functions as probabilities and assign the point to the tissue with the highest probability. In the end, we only want to visualize all points belonging to the muscles, while points belonging to fat should be invisible. A common solution to this problem in computer graphics is volume rendering. We store all the information like vertex positions, normals, muscle, and fat functions about each tetrahedron on the GPU and perform raycasting via ray propagation inside the fragment shader to render the muscles. So just to be clear, we do not perform any meshing operations when user creates or edit the muscle curves. We simply compute muscles and fat functions and perform volume rendering using shaders to visualize our segmentation. The line image you see on the screen is an example of the volume rendered muscle. To provide an additional control over the muscle shapes, we allow users to change the rate of diffusion along certain directions. This is achieved by introducing a tensor field that biases the directions in which tissues diffuse at point in space. Tensor field is represented by a tensor matrix AI that we previously saw in our formulation of anisotropic Laplacian. We provide an easy way for the user to construct the tensor field for the individual muscles. The first point of each muscle curve is assigned a 3D frame representing eigenvector of a tensor. The first vector in the frame is always aligned with the curved tangent, while the other two eigenvectors lie in its null space. We provide an easy way for the user to construct the tensor field for the individual muscles. The first point of each muscle curve is assigned a 3D frame representing an eigenvector of a tensor. The first vector in the frame is always aligned with the curved tangent, while the other two eigenvectors lie in its null space. The user has control over the rotation of this eigenvector, and additionally the user can control the magnitude of eigenvalues to bias diffusion rate along each of the eigenvector directions. Given the complete muscle curve network and the corresponding muscle functions defined over the volumetric domain, we need to extract the geometry of the muscles suitable for downstream applications. Isosurface extraction methods do not trivially solve our problem, because we are not simply extracting an isosurface of a scalar function. Instead, we want to compute a pointwise maximum of multiple scalar functions inside each tetrahedron, and extract the boundary separating each function while ensuring the final output is a manifold tetrahedral mesh. In other words, inside each tetrahedron, each tissue function can be thought of as a pointwise vote for ownership, and we want to split the tetrahedron along boundaries that delineate change in the maximum vote and assign each subset to the tissue with the maximum value. We cast this problem of extracting the muscle surface geometry as a solution to the computation of the upper envelope of scalar functions representing each tissue over the tetrahedron. First, let's look at a simple example of the upper envelope problem. 4 line segments are defined over a 1D domain from A to B, and the upper envelope is the pointwise maximum of all segments over the domain. The maximization diagram is a subdivision of the domain AB into cells, where each cell's identity is induced by the upper envelope. Alternatively, we can think of the maximization diagram as the projection of the upper envelope onto the domain. Let us now define the general upper envelope problem. Let S be n D simplices in D plus 1 dimensional space. D simplex has D plus 1 vertices. In other words, D equals to 1 is a line segment, D equals to 2 is a triangle, and D equal to 3 is a tetrahedron. We can thus view each S of I as the graph of a partially defined linear function whose domain of a definition is a D-simplex. The upper envelope M of the given simplices is the point-wise maximum of these functions. The maximization diagram is the subdivision of our domain into connected cells obtained by the projection of the upper envelope onto the domain. And if you remember how we formulated our volumetric segmentation problem, then you will see that it is identical to solving the upper envelope problem. In our case, we are interested in finding maximization diagrams of all tissue functions over the volume constrained by the surface of the skin. This problem can be solved by considering finding the maximization diagrams of the tissue functions over each tetrahedron separately, in which case, in contrast to the general upper envelope problem, we restrict our domain by 3-simplex. Here on the left, you see an example of the maximization diagram of the functions defined by scalar values at the vertices of the tetrahedron, and on the right, you can see the tetrahedronization of each cell. As a result, the original TET is split into more subtets, where each subtet has only one function, that is the maximum. In other words, we can assign the subtet to one of the tissues. Performing this operation for every single tetrahedron results in the new tetrahedral mesh, where each tetrahedron is assigned to one tissue. We can extract individual tissue shapes by simply combining all tetrahedrons that are assigned to that tissue. Here's a simple example of taking a uniform 3x3 tetrahedral mesh with two scalar functions defined over it and splitting it into two tetrahedral meshes. The split is the result of computing tetrahedralized maximization diagrams of every tetrahedron. Now let's discuss in detail our algorithm for computing manifold tetrahedralized maximization diagrams of functions defined as scalar fields over the vertices of a tetrahedral mesh. First, let's define auxiliary functions called prone tissues. Assume we have a set of tissues functions defined over our tetrahedral mesh that we already computed. We notice that if some tissue functions f of I is strictly below any other tissue function f of j, then it will not be part of the maximization diagram and therefore can be ignored to help avoid unnecessary computation. We define a sparse matrix W where ijth entry is 1 if and only if there exists at least one tetrahedron whose maximization diagram will contain cells assigned to tissues I and j. Next, let's define auxiliary function split tetrahedron. Assume we are only considering a set of two tissue functions. Then we want to find the tetrahedralized maximization diagram that results from computing the upper envelope of those two functions. We simply define a new function f3 as the difference between f1 and f2 and split the tetrahedron along the isovalue of 0. We find a set of sorted unique edges of the TET that are intersected by the isosurface of our function. The number of intersected edges is usually either 3 or 4. We then define a split edge operator that, given a TET and an edge, first splits the edge at a vertex and then splits the TET into half along this vertex and vertices on the opposite edge. We simply run split edge recursively on each edge to produce the resulting TET mesh. The order in which we split these edges determines the final topology of the tessellation. By simply sorting the intersected unique edges, we solve the potential problem of inconsistent tessellation between adjacent TETs. Here we see an example of a maximization diagram that is defined over two adjacent TETs with vertices 1, 2, 3, 4 and 1, 3, 4, 5. During the tessellation, there is no guarantee that the shared face 1, 3, 4 is split the same way. By making sure the order of edge splits is consistent, we can guarantee that the face is split the same way. Now we are ready to define our algorithm for computing tetrahedralized maximization diagram. Our inputs are the TET mesh and tissue functions defined over this TET mesh. Our output is the new TET mesh and tissue labeling vector L for each tetrahedron. We first prune tissues, then for each tissue we find a set of tissues that intersected. Then for every pair of intersected tissues, we iterate through every TET and we split it necessary along the isovalue of 0 of the new function defined as the difference between two intersected functions. Finally, we update our TET mesh with the new split subtets. And in the end, every tetrahedron is now guaranteed to have exactly one maximum function defined over it, which becomes our labeling vector. And here's an example of the final tessellation produced by the upper envelope algorithm. Because our volumetric domain is represented as an unstructured mesh, the resulting topology of the muscle meshes ends up containing skinny tetrahedrons. However, because we guarantee that the resulting meshes are manifold, it is straightforward to extract the boundary faces. The resulting muscle surface triangle meshes can be easily remeshed and tetrahedralized again. Finally, here are some of the results of exported geometry. Although we demonstrated that our tool enables users to create complex musculoskeletal geometries, there are limitations subject to future work. First, the quality of the muscle shape depends on the quality of the tetrahedralization. Coarse meshes prevent the creation of smooth and thin muscles, yet high-quality meshes can affect the performance of computing muscle functions and hinder the interactive experience. Each muscle is represented by a single curve, which limits the user from creating some complex muscle shapes with multiple origin and insertion points. And additionally, there's a lack of control over the pennation angle.